Okay. No, it's supposed to problem. Potential difference between here and here is phi sub e. We don't care what it is. Okay. I mean, yeah, maybe we do, but not in this case. Okay. Maybe it's 10 volts. Maybe it's 10,000 volts. Doesn't matter to answer the question. Okay. This depicts diameter of one, or a wire of one diameter. That's a 4 millimeter diameter. This is a 1 millimeter diameter. Same material. So, for example, you have the same number of electrons available per cubic meter or cubic millimeter or whatever you want to talk about. Okay, the density of the electrons is identical. Of course, the diameter is different. Now, let's say the electric field in the thicker wire is 10 newtons per coulomb. Question then is, what's the electric field in the thinner wire? And the key fact is the current's the same in both. So first question, just to start getting our heads around it a little bit, is in which wire do you need the bigger electric field? Okay, we did pretty well with this. Okay, what it comes down to is if you have more electrons per square meter or per cubic meter or per cubic millimeter, whatever, that you have the same number per unit of volume, which would be the same number per unit of length of the wire. Well, no, I'm saying that wrong. Same density of electrons. And intuition said that, well, they got to move faster here because there aren't as many of them. That's the simplest way to look at it, okay, without getting into too much detail about how much faster or how much more electric field, okay? Get the electrons to move fast, remember that they're accelerated by the electric field, okay? But they don't get to accelerate far, they just kind of wiggle around, bounce back and forth, but gradually tend to move in the direction the electric field pushes them. Now, for an electric field here with a higher potential here than here, your electric field's in this direction. So electrons are actually moving in this direction, but your current is in the direction of the electric field. Okay? And we'll deal with that. That's a little counterintuitive, but it's not hard to understand. But right now, this idea is simply that more electric field puts more force in the electrons, so that between collisions, they gain more speed so that whatever drift they have is faster. Okay, so we can say, okay. Electrons drift faster here. If they didn't, they wouldn't be able to use a not quite great analogy, but they wouldn't be able to maintain the whatever flow there is from this one, okay? Maintain the same current, they've got to drift faster because there aren't as many of them. Okay. How much faster? So my question is, how much faster? What are your thoughts on that? Okay, well, what it comes down to is how much faster. You've got 16 times the cross-sectional area here that you have here, because the cross-sections are circles. And I'm just going to make a quick note because we had some real problems with this. have circular cross sections. So the ratio of the areas of two circles is, well, the area of a circle is pi r squared, which we didn't get. Okay, we got to get that. That's got to be just part of your knowledge of the universe. You have pi r2 squared over pi r1 squared. That's the ratio of your areas. So that reduces r2 over r1 squared. In this case, the ratio is 4 in this case. Okay. So you get 4 squared or 16. That's why they got to go 16 times faster here. Okay. Now you really have to lock that. You have to understand that at the level of just intuition. Okay. So you really want to stop and think about this. It's fundamental to what goes on in circuits. Okay. So now we got 16 times as many electrons, got to be 16 times faster. Okay, now. Sixteen times faster requires 16 times the average force. And you can actually derive that. The distance these things travel before they collide and have to basically start over, or on the average start over, is going to give you 16 times the acceleration. Okay, and 16 times the acceleration over given distance. It's going to give you 16 times the average velocity. Okay, it just comes back to uniform acceleration. That's complicated because these things are moving in random directions and you're talking about the acceleration only in one direction, but it works out. Okay, so you need 16 times the electric field. Okay, well, if you need 16 times the electric field, then the question becomes, how is the potential difference distributed between here, here, and here? But let's just say, just for starters, let's say these three segments all have the same length. Okay. So let's call this L1. L2 and L3. What's the potential difference across each in terms of phi sub e, which is total potential difference here? In other words, how is a potential difference split up between here, here, and here? Or not? Okay, I don't remember if I drew the picture before or after applause. If we can kind of picture this schematically by electric field here, electric field here, electric field here, right? Of course, we see pretty quickly that the arrows are not quite right because the electric field here is 16 times as great as these, right? So we'd really want more like, if this is this long, and this is only going to be a little tiny. That's the shortest I can make it. It needs to be even shorter, right? Okay, this is schematic, this is actual. Okay, and this is closer to actual. Okay, this is like maybe 1/8. Okay, so how is potential difference related to the electric field? Well, how's the potential difference related? What is the relationship between? Okay, got a good answer there. The answer I got, now the answer I would ultimately hope for is that the potential difference is, or the electric field's a gradient of the potential difference, but we'll relate that to the answer I got because it's a very simple relationship. Okay, so the answer I got was you multiply the electric field by the distance to get the potential difference. Okay, so okay, which is really okay for constant E if your delta S is in the same direction as E. See dot delta S, and if you understand the dot product, then you really need to be sure you do. You understand that this is just a component of E in the direction of your displacement. Okay, going to be parallel to your displacement. And of course, you got your plus and minus sign because your delta phi can be positive or negative, but that's easy to understand. Okay. Really ought to think about what I'm about to say before I start writing. But I want to write it this way. Great. And of course, the gradient in this case, when everything's in the same direction, just becomes a derivative with respect to position. Okay, one dimension, it comes down to this, and a gradient comes down to just a derivative with respect to displacement, okay? Derivative with respect to position along the line. And if he's constant, then the derivative is just change in phi divided by change in s. Now you need to understand that all the way back to the theory of calculus and why it's true, okay? But yeah, and if you do, you get deeper understanding of the calculus, you can understand physics a little bit, okay? Yeah, your intuition is great, okay? You're missing some background, okay? Fill in the background and your intuition is going to take you a long way. Okay. And of course, most people come out of calculus have to think about this, okay? Because the gradient stuff we do in multivariable calculus that we've been through is something we usually don't reduce down to a constant vector field along a straight line. Okay. Although I kind of think your materials might have done that. Okay, one or another. There's our big idea. So using this idea with the fact that this is 16 times greater than this or this, can you find a potential difference across each of the three segments? Again, fill in a few little blanks and you guys do real well. Your intuition's good. Get those facts. Put that background stuff. Okay. E is then, well, I'm going to just write it as this. Do that, right? If L is the same for both. You know, if they're different lights, it's really easy to adapt that. You put an L1, an L2, and an L3 there, right? Well, then this equals I'm not going to put the vector over L. We're just going to write as EL where E is equal to E1, which is equal to E3. And of course, we've already established D2 is 16 times that. 18 eels. Okay. Proportional potential difference in the thinner wire is 16 EL over 18 EL, which is 8/9. Okay. Okay. Now we're just continuing what we did before. where you had same electric field and these two, and 16 times the electric field in the middle. Okay, so we came up with the delta pi of 18 EL. We get delta pi over 18L, right? L is 20 centimeters, so 18 times 20 is 160. Okay, 320 centimeters or 3.2 meters. So this is going to be okay, 12 volts over 3.2 meters. Now let's see, 12 over 32 reduces down to 3 over 16, which is 0.1875. So it ought to be about, and that's not even right. What did I do? Well, anyhow, okay, it's going to be roughly about 3.7 volts per meter or 3.7 newtons per coulomb. So that's it. Now, in general, diameters are D1 and D2, lengths L1, L2, and L3. What can you conclude? That still E1 equals E3. E2 equals E2 equals D1 over D2 quantity squared E1, where D1 is the diameter of the first wire, D2 diameter of the middle wire, right? And the diameter of the end wire is the same. Okay. So there are electric fields. You get something very much like this, right? Because again, you're just multiplying the electric field by length, and it should be L3 here. Okay. So electric field times the length of L1 and L3 because it's the same electric field in both of those, right? And then the greater electric field in the thin wire, assuming the middle wire is the thin one, okay? Times E times L2. And if you have D1, D2, and all that stuff, it's still really easy to figure out what the electric field is if you know what delta phi is. Okay. So now, big concept. current density.
You see.
Current density is current per unit of cross-sectional area. Now, current is charge passing the point per unit of time. SI units, coulombs per second. Or amperes, that's what an amp is. Okay. Now, coulombs used to be your fundamental unit. You can measure charge to several decimal places. Okay. Now, amperes is a fundamental SI unit because it can be measured more accurately. Okay. The best measurements come from measuring amps and then including coulombs, so forth. Okay, so coulomb is defined in terms of amps rather than an amp defined in terms of coulombs. You see that? Kind of important. Okay, those are your SI units. And then current density. In what unit would you think current density would be measured? Okay. Okay, well. Another really big idea. And I think I'll go to the longer board. Yeah. Yeah. Okay. Central idea now. There's resistivity. Again, I use it on. Resistivity. Relates electric field and current density. Tells you how much current density you get if you know the electric field. Okay. resistivity is. Or density over electric field. Current density per unit of electric field. So what would the units of resistivity be? Okay, I think I might have heard a really good answer, but it went fast enough that I couldn't process it because I haven't worked it out yet. Okay. But current density okay, amps per meter squared divided by newtons per coulomb if you want, right? Could come out something like this. And other ways of writing it. Okay. That might have written it wrong. Units are a little bit complicated, but you can easily get the units by taking units of current density, which is amps per square meter, and dividing it by electric field, which could be joules per coulomb or joules per meter or newtons per coulomb. Okay. Wait a minute. It's a joules per meter. And it's not digital. Okay. Okay, anyhow. These are your fundamental concepts. Okay. These are fundamental concepts. If you look at the chapter summary, the first two things are current and current density and resistivity. Okay. And everything else kind of follows from that. Now we're almost out of time. We spent more time than I anticipated doing this. I want to get to resistance. And I guess I'll actually want to develop it in terms of basic meanings. Otherwise, you just revert to less comprehensive concept. Okay, you just revert to Ohm's law and forget about everything else. Okay, I don't want you to do that because, of course, I'm going to test you on this. I'm going to, yeah, you'll have to know Ohm's law. Okay, it just comes from resistivity. Then I want to use typical values of resistivity to do this, and we don't have time left. Okay, so we'll pick up on this on Wednesday.